Okay, so yeah, this just demonstration, we're not gonna be able to actually do that because we have very low capacitance in this system, but we've got two capacitor plates. We've got a couple of leads. Now, those leads are just dangling, but they could be attached to a power source, and there could be a switch. So let's say these things are discharged. They're just discharging through my fingers. And didn't create much of a burn. Okay. Okay, that's that. Okay, that's better. Okay, so it's a discharge capacitor. Now I throw the switch, and what's going to happen? Well, those batteries are going to pull negative charges off of here because it's negative charges that actually are going to move around. Okay, it's going to pull negative charge off of this plate because it's attracted to positive. Now it's going to pump those over to the negative side. That's what the chemicals do, and deposit them on this side. Okay, well, the first charge gets deposited, and the voltage between here and here is, say, 6 volts. Okay, now first electron arrives over here. Actually, electron doesn't go from here to here. You know, electron pulls off of here, which creates an electric field here, and one electron goes on. Okay, so sometime the first electron arrives over here. So now you have a -1 electron charge here, +1 electron, +1 electron charge here, -1 electron charge. Okay. QE. Okay. Charge QE, charge negative QE, which creates electric field between these plates because there's a voltage and all that stuff. Divide the voltage by the separation, get the electric field. Or you use Gauss's law and understand why the electric field here, because of symmetry being perpendicular to the plates, would penetrate a Gaussian surface here in such a way that you get a certain electric field. Okay, well now the electric field is going to be opposed to the battery, so you're going to have a little less voltage. And then another electron comes along and pulls that electric field. Now it's not a very big electric field. It's going to be really negligible compared to the voltage of the battery, the voltage that you get from that field. And you want to understand every detail of that. But the point then is that as charges get transferred here, the charge on these plates increases. And with every increase in charge, you get a voltage across this capacitor that opposes the voltage of the source, the power source, the batteries in this case. That's what we're using. Okay. So that you have less voltage between here and there with every new charge, which means you have less current. So the charge builds and exponentially approaches the charge that would give you a 6 volt potential difference between these plates, opposed to the 6 volts of the battery, at which point that last electron finally gets there and the current ceases. Okay. Okay, let's think through all that. You understand electric field, wire, all that stuff. But we wanted to just make sure we understand what's going on here. So we talk about displacement current. Okay. Now we've got Ampere's law. It says that if you integrate the magnetic field around this wire, for example, what do you get? Okay. Well, you get a multiple of the current. Okay. They're not going to worry too much about what the multiple of the current is. You can work out the details of that. You got the formulas. So let's not confuse ourselves with that. It's some constant times the current. The constant's, you know, related to the 10 to the -7. Well, we won't get into that. Okay. And it's related to the fact that, just to kind of review, the current in a little increment here makes a contribution to the magnetic field over here. It's K prime I delta L cross the R vector. Remember that. Okay, we use that to derive what the magnetic field circling this wire would be. All right, and let's see now if the current electrons are moving in this direction, current's in this direction. So by the right hand rule, current surrounds this wire in the clockwise direction. Just part of what you want to understand when you look at this. Okay, Ampere's law says, again, if you integrate around here, you get a multiple of the curve. Okay. Now, if you integrate around a circle between these capacitor plates, there's no current in here. Okay. So you think you would get zero. Turns out you don't. Because if you did, well, we get a contradiction. Let's look at the contradiction. Clearly, if you integrate around here and use current, there's no current between them. And you're going to get zero from the current. Okay. If you integrate around a path right on the surface of this conductor, of this plate, well, there's no current flowing through this plate. Current doesn't start till you get to the extension of this wire. Now, the wire is attached here, and it's attached to a bolt that's then a conducting bolt that's then attached to the plate. Okay. Now, if you integrate along a surface just outside of this plate, then you enclose a current. But if you're right on the surface of the plate, you don't enclose a current. It's not going to change that quick. The result is that you have to have what's called a displacement current. Okay? And the displacement current is just related to the electric field within here. You have an electric field flux. Very easy to find the electric field flux. Whatever the electric field is at a point at a time, it's pretty much uniform between these plates. You just multiply by the area of the plates and you've got the flux through a surface between the plates, surrounding the plates. Now I can't really surround the plates because of this, but you get the idea. Okay, just take a surface, same size as the plates, circular surface, parallel to the plates and with the same axis. All right. So that what we call displacement current between these plates creates a magnetic field that we can integrate around a loop. And the integral has to be the same as it would be around one of the wires. Now I'm going to attempt it. I don't know why I've got my glasses on. See that capacitor just fine. Okay. So let me pause and get the board set up. Oh, okay, so let's go ahead and draw the picture before we try to explain it. So we have two plates, white circles. We have a wire coming into this plate and then one coming out of this plate. We have a loop between the plates. It's a purple loop here. It's a little bit faint. We should be able to see it. And a loop right on the surface of the plates. And implicitly, we're going to say that, well, since the current is in this direction, those loops are going to run this way. Okay. Here's a side view. Now, the electric flux, with which we should be familiar, is just D times A. A is the area of each plate. Okay. Then let's have one more of them. around the wire. Okay, Ampere's law. Says the integral of B dot, uses L and multivariable calculus often use like DS. So it's the same thing. Okay, just different symbol. The integral around. Okay. Equals a multiple of I plus a multiple of phi. Phi sub t. Not worried about the constants. All we're saying is that around this loop, calculate it based on I, because this loop surrounds the wire and there's no electric field. The field's confined between the plates. Ideally, okay? Doesn't have to actually get out there, but it's pretty nice. You don't have to get far from the plates before it becomes totally insignificant. So just go away from the plates. Okay, so we have that. On the surface of the plates, we're not surrounding a current in the wire. Or let's say just inside the surface. Okay. So here or between the plates, we have no current. So we can't say the integral B dot dl is this. Okay. It depends on the flux between the plates. And closed flux, the flux enclosed by the surface. Okay. That's an important idea, and it's the idea that your homework actually starts with. So it develops that whole idea. You worry about the constants, but that's the concept. The formulas are not difficult to use. Okay, now what I said is not quite right. No better. And it's doing this a little more in a little more detail. They're shown that these don't work out. You just use phi d. It's multiple of derivative of phi d. And this multiple is called the displacement, right? Now, what's happening? If you think about it, as the capacitor charges, what happens? The current decreases because you have the voltage across the capacitor, which is opposed to the voltage of the source. So the current is decreasing. That means the electric field changes in time, and it's increasing, but at a decreasing rate. Because you get less current, charge builds less quickly, so the electric field increases less quickly. Okay? So, that's a hand-waving explanation at this point, but the symbols are simple. I mean, symbol here is an epsilon naught, okay? And again, we're not going to worry about the details of that just because we have kind of limited time to be able to work that through, get the formulas, get the constants here. Okay. So there we have it. I will say on the exam, I'm not going to give you the formula for this. But somewhere I'll write out d pi e dt with the constant in front of it. So if you know this much, you'll be able to see where the constant is. And I'll even write the constant for Ampere's law, but I'm not going to tell you what it is. Okay? I'm just going to say it's an R bar times I, whatever an R bar is. Okay? I'll tell you specifically what it is so that you don't have to worry too much about memorizing a bunch of constants. Okay? Concept is what's important. Multiple comes out in terms of constants. And of course, you can always go back. And I'm not going to tell you what the constants are on QV cross B. And I'm not going to tell you what the constants are on IL cross B. Okay? I'm not going to tell you what the constant is in the Biot-Savart law. Okay? Those are fundamental. And the constant, where does K prime come in? Okay? That's really what it comes down to. What is K prime? Where does it come in? And I might tell you things like K equals 1 over 4 pi epsilon naught. K equals 4 pi mu naught. Because it's tricky to remember where the 4 pi's are. Theoretically, you ought to be able to conclude that based on your knowledge of molecular calculus and Stokes theorem and divergence theorem, which we're going to begin to start tomorrow. Okay, but we don't require molecular calculus. So I'm not going to require you to know all the details of how those surfaces. You'll need that if you're in electrical engineering, but you'll get very used to it there. Okay. I'm not giving you formulas, but I will give you expressions with the appropriate constants. And if you know what the relationships are, you'll be able to write down the formulas. Okay. Let's move on to some more examples. Okay, you got Maxwell's equations. First equation is Coulomb's law, essentially, but in the form of Gauss's law. Okay, Coulomb's law says this. This says that the integral over a surface of E dot dA. In other words, the flux of the electric field through the surface 4 pi K times the enclosed charge X like epsilon naught here. I like K because it's easy to remember. 9 times 10 to the 9th, and then the units that take all this out in newtons, which is going to be Newton meters squared per Coulomb squared. Okay. Okay. And that's the enclosed charge over epsilon naught. Now, these two things are equivalent. All you got to do is remember one of them, you can get the other one. No, we can solve this for epsilon naught, and this is what you're going to get. Or you can solve this one for K, and this is what you're going to get. So, I like this because it invokes the idea of the surface area of a sphere surrounding a charge. Okay? And that's the way we first developed this thing. All right, well, that's it. Okay? What are we using? Gauss's law for magnetic fields. And you're going to understand this instantly if you understand that the line integral that the divergence of curl is zero. Okay, really just comes down to that. So, okay, this is Gauss's law. For electric fields, I'll just use a G, as you know what we mean by electric field. Okay, now, this B is a curl of a vector potential field. Del dot B is zero. That's the way I would state it. To anybody who's taking all over the calculus. Now, all you got to remember is del dot B is zero, but this is one. Okay? Because any magnetic field's a curl of a vector potential. I'd like to talk about that, but it's beyond the prescribed scope of this course. I've got a guy that owns a property, uh, a few acres of property. It starts just across the street, about 25 feet from my property ends at the beginning of the street. And see him out mowing. Okay. First, he's out there mowing with hand mowing. Okay. And it's about 3 acres. Okay, and it's on a steep hillside. Guys, looks to be roughly my age. It turns out he's about 3 years younger, so just a young fellow. But so I waved to him. Eventually, over a few years, we ended up talking. I mean, he was busy. I didn't want to interrupt him, and he didn't really necessarily look like he wanted to be interrupted. Good guy. And it turns out he's got a master's degree in physics from Stanford. Okay, that's kind of top of line master's degree. And he hasn't used his physics. He's in real estate. He started out with some jobs in physics, but turned out he just used his brain to make money in real estate. He's very good at it. He's got a lot of properties near where I live. He's a good guy. He and he said, "Oh, I think I remember something about Maxwell equation. Let's see." I was at the beach, and there's this guy with an MIT shirt on. So I went up to him, said, "Del dot B equals zero, right?" The guy thought for a minute and said, "Yeah." It's about all I remembered about Maxwell's equations. He read it for 15 minutes. He'd understand them all. Just haven't thought about them in years. I get to think about him every year. So. He's, I think, a good notch smarter than I am, maybe 17 notches. I don't know. As you know, you can find your notches. Okay. And then you have the one just kind of listening almost in order that you see them. This is called Faraday's law. I haven't really used it. Okay. Electric field is the time derivative of your magnetic field. And it's not the electric field, it's the integral of the electric field around it. Okay. Integral of the electric field around loop. And we've used that. We've used that to figure out the electric field. Uh, so there, we got that. I did put the negative sign in there. Okay. And then we have Ampere's law. Uh, and that's the one we have here, and if I am not write it out. And this is it. What's the multiple? Your multiple is mu naught times. I think your text uses a small I. I don't like to use the small I because a lot of things we do in physics rely on the unit vectors I, J, and K. And it's too easy to confuse them. So I'll generally use a large I, and the text pretty much does the same thing. And then the other one is epsilon naught, which is like 1/4 pi K. D phi dt, and this is of course the magnetic field. That's how we draw a variable constant. So your multiple of d phi e dt would be mu naught epsilon naught. And very reciprocal of it. Yeah. Okay. There you have. Now, these are all differential equations, but they're not differential equations that we're equipped to solve at this point. But they do give you everything that we can do with electromagnetism. This is the whole thing. Everything comes from these four laws. Now, the way we approach things, you know, we start with like QV cross B. Which is pretty much a result of Ampere's law. Okay. You got a wire, you got symmetry around the wire. You integrate the magnetic field around the wire at a constant distance. It's got to be this, and that comes directly from the QV cross B or IL cross B. Okay, so you want that perspective because again, it summarizes your most basic laws. Okay, Gauss's law is equivalent to this. We won't really use this one, but it really comes down again to the fact that you have no monopoles. Okay. This bothers me a little, not much. Okay. Okay, now remember our old friend from first semester? Okay. Yep. This thing is rotating. Okay, this is a conductor, it's steel. Okay. Good conductor. And let's just say it, I mean, there is a magnetic field. Yeah, there is a magnetic field, okay? But there's magnetic field is pretty much in the north-south direction, okay? Let's say we had a magnetic field straight down. Okay, we got a big old Helmholtz coil, big old coil above us, big old coil below us. And we're running thousands of amps through it, so we got this huge magnetic field, okay? So we've got a 1 Tesla field. We want to think of a strong field. We're not going to actually do that numerically. Okay. Now, what's going to happen to the charges in this wire? And take it in this beam. Okay. You got electrons that are free to move, right? Are they experiencing a force? Okay. Now, let's say this thing is stop action. This is thing is stopped right now. It's moving in. Okay, this point is moving in this direction. You've got an electron here. In what direction is it moving, and in what direction does its downward magnetic field accelerate it? Or what direction is the force of that magnetic field? Okay, so we had a little discussion because people get a little confused. Remember that QV is a product of Q and V. And since Q is negative, the direction of QV is going to be opposite to the direction of V. So V is this direction, QV is in this direction. Okay. Now, inconveniently, your magnetic field is down. Okay. And we turn the magnetic field toward the direction of QV, which is here. And we conclude that that electron is going to be accelerated this way. Okay. Now, it probably won't be accelerated that way, and certainly won't be accelerated that way for long, because what this is going to do is it's going to cause a migration of electrons from this end toward the center, right? If the electrons are experiencing force in this direction, then you're going to end up with electrons kind of jammed up at this end and more rare at this end. Now, there won't be many at the speed this thing's going. Even if we had a real strong magnetic field, you wouldn't have a whole lot of separation, but you would measure then the voltage between here and here. Okay. So maybe you could set up a meter between here and here that's spinning along with this thing. It might be tricky to set up a meter that wouldn't respond to that strong magnetic field, but maybe you could engineer it. Okay. This is future engineering. You might even think about how you would do that, because that's, especially if you're in mechanical or electrical engineering. Okay. Okay, what's going to happen on this side? What's going to happen to the electrons on this side? Well, their QV is going to be here, right? So magnetic field is again down. QV is in that direction, so you're going to have the force in this direction. So electrons on this end will also be accelerated toward the center. Okay. Now, pretty soon, if this thing keeps rotating at a constant rate, you're going to reach a steady state where the repulsion of the electrons balances the magnetic force trying to push them toward the center. So you're not going to end up with many electrons at the center, and you're not going to end up with much unshielded positive charge here, but it'll be enough that you could measure quite easily, I think. You'd end up with a significant voltage. It doesn't take many electrons to create a significant voltage. Okay. And you go back to Coulomb's law and figure out how that works. Okay. Just looking for pieces that can simulate this. Now, let me pause for a second. Okay. Okay, look, I've got this set up here. Now, this represents, these are wooden meter sticks, and obviously they're not conductors. But let's just use our imagination and see these as metallic conductors, okay? And now, the end, probably should have picked something that doesn't roll so easily. Okay. Okay. Probably gonna have trouble just here. Okay. Add, I don't have enough hands. Okay. At the ends, let's just say that I'm a battery. Okay. So now, my right side of my chest is positively charged and the left side is negatively charged. Okay. And these things, these meter sticks are metallic and they conduct electricity. So in what direction am I going to get a current? Okay, right side of my chest is here. Okay, left side is here. What will be the direction of the current? Yeah, it's going to be clockwise. Okay, so it's going to go start here and go around like this. I have to just with my head and my neck, my greater shape. But anyhow, there it is. Okay. All right. Now, what if we have everything fixed? I'm stationary. We got these rails here, all these 2 meter stick rails. These rails are stationary, they're attached to some structure. Okay. But the actual metal rod here that's now kind of, let's see, now I'm not going to try to drop it. But this metal rod is in contact, completes the circuit. Okay, so if the magnetic field is downward, in what direction is the force on the current in the sliding number here? Okay, in the round rod. Okay, so that's what it looks like. I probably better draw it so we can talk about the measurement and stuff. So let's just say that here's positive, here's negative, and let's say I said the right side of my chest is positive. Go this way. Okay, so here's a battery. It's attached to this rail. That's one of the meter sticks. And plus minus it belongs. Unless put the plus to it belongs. Okay. No, one of the plus there. But okay, let's try again. Okay. So we're gonna have plus here, we're gonna have minus. And we got the rail here. And we got um so-called free being here. By free, it means if you move along this rail, staying in contact with it, okay? If there's a force that requires it. So we have a current. And now if we have a magnetic field B, into the board, and the force in the beam is in what direction? Okay, I'm doing a lot of things today without thinking clearly. That's correct. If QV is in this direction and B is in this direction, then the force is QV cross B, not B cross QV. I went ahead and did B cross QV and got this, okay? But QV is in this direction and B is in this direction. So, look, can't even get my hand right, but you understand that QV is here, B is here, turn this toward this, you're going to get a force in this direction. So what I said was totally backward. Okay. So if QV is in this direction, B is in this direction, force in the electrons is in this direction. So you're going to get electrons on this side and unshielded positive charges on this side. Okay. So I said that totally backward without thinking. And in this case, I was doing B cross B, and it's B cross B. So your QV is going to be in this direction. It's going to be in the direction of I. So that's your IL. Okay. Or your I delta L are in this direction. And if you cross a vector in that direction with a vector in this direction, you're going to get force in this direction. Okay. So capital L full name. Okay. If you reverse the current or reverse the magnetic field, let the magnetic field come out of the board. Let's do that. So I'll have to redraw the current. Okay. Okay, so if these out of the board, this is basically the principle of a railgun. Very simple idea. You put a lot of current through a rail, through this cross piece. If you got a magnetic field, that's the coils above, coils below, whatever it takes. If you've got a magnetic field, you can get a lot of force. Okay, I just want to stretch things a little bit. One reason I went to this is because I love this apparatus. And I start first semester with this apparatus, and we do measurement of rotation motion, which we can do in real time, and it doesn't get out of hand. And we can measure it with just a stopwatch, or even, well, we measure not having to use any sophisticated equipment. Whereas if you roll a ball down the ramp, you need much more precise equipment to get the uniform acceleration and stuff. Okay, well, that's a whole different story. Okay, let's say I move this rail here in this direction through downward magnetic field. Okay. Now, if I'm moving it in this direction, then the electrons, QV, V's in this direction, friendly electron, and QV's in this direction. And QV cross V is in, wait a minute, I've got it backwards here. Why? How come I have it backwards? QV, maybe I ought to move it in this direction. Then QV would be here, and V would be here, and it would be this way. But since I'm moving it in this direction, it's opposite, so I can't move my hand like that, so I can't move it straight up. Yeah. Okay, point is, I'm moving the thing in this direction, what we saw before, after I corrected it. Electrons will be pushed in this direction. So you're going to end up with positive charge here, negative charge here. All the electrons are going to feel the same force, aren't they? So they all feel the same force, so there's the same potential gradient along here. Because, of course, potential gradient is the electric field. And you multiply the electric field by the charge, and you get the force, which is also QV cross V. Okay? So as soon as this thing reaches a steady state, which it will very, very, very quickly, okay, in a nanosecond or so, after achieving full velocity. And I'm just guessing about the nanosecond, it seems about right. In the case where this thing is rotating, it's not linear. Why is it not linear? The gradient isn't linear because the force on the electron is not linear from one end of the rod to the other. Why is it not linear? Because the electrons here are moving faster than the electrons here. Okay? In other words, your speed at distance r is r omega, right? You know, distance from the center times your angular velocity, just by the definition of a radian. And if you can't invoke the definition of a radian and explain that, please learn to. Okay? It saves a lot of, takes a lot of mystery out of a lot of formulas. Put it that way. Okay. So that's a very interesting situation. You're not going to have time, I know, because you need the rest of the time in the semester. So you're not going to have time to think that one through, but it'd be worth thinking through it some. What's going to happen to the electric field in here? And clearly, since there's less force on the electrons near the center, there'll be less electric field in electrons near the center. Because the electric field is going to very quickly, if the thing maintains a steady state, steady constant rate of rotation and a constant magnetic field, then the force on an electron is going to depend only on how far it is from the center. It's going to be less because the electron's not moving as fast, and the force of the electric field is going to have to be equal and opposite to the magnetic force. Okay, so that's kind of it. All right. Okay, recall we started out talking about magnetic induction in terms of what is called mutual inductance, which is actually the topic of chapter 30 rather than chapter 29. But I still think a kind of a piece. So I don't necessarily regret having done that. I think it was a good introduction. Remember what we did was we put this inside the Helmholtz. Okay. And then we created a current. Okay. In the Helmholtz coils, which created a magnetic field. So that magnetic field created a magnetic flux through this loop. Okay. And as the current built, we got a current in this coil. Okay. I don't know whether to call it a solenoid or a coil. It's not really tightly wound, so it's not just almost a circle. Okay. It's got some length, but it's not so long that you don't have a lot of edge effects. You want to think about that. So this is kind of a coil slash solenoid, which is how I refer to it, I think, really. So that's an example of mutual inductance. And if we have an alternating current, then as the current in the Helmholtz coils goes up and down, the magnetic field here changes direction, changes from this direction to this direction, okay, from this direction to this direction, assuming this thing's aligned with the axis of the coils, okay, Helmholtz coils. So that your magnetic field is continually changing, so that the current in here is continually changing. And the kicker is, ultimately, that the current in here creates a magnetic field opposed to the change in the magnetic field due to the Helmholtz coils, which leads to interesting differential equation. I'll talk about a little bit in lab, just to refresh you on the very first early linear homogeneous differential equations that you pretty much started your differential equations course last fall with. Okay, naturally it says was properly constructed. So that's the idea. Now you just want to start with that idea. You just start looking at chapter 30. And since we got toward the end of the semester, I really, and since we're going to be done with chapter 30 a week from today, and we're not going to have any more class after that. Recommend that you get a little head start reading chapter 30. Just scan it 30 minutes if you can find the time. Okay.